I'd like to thank you all for coming to our third lecture of Phyllis and George Halburn Radio Astronomy Lecture Series that we've organized in the last few years. This series is supported by the Halburn family, and videotaping of this series is also provided by our department chair, Michael Schmidt, who supported basically the cost of videotaping the series. So for your information, we have a videotaping of all the talks, actually just video and audio taping of all the talks that we've had in the last 3 years on this website. So if you're interested, you can always go back to listen or watch past lectures that we've had in this series. Today we're pleased to welcome our distinguished speaker, Professor Imke de Pater from the University of California, Berkeley. She's a professor in the Department of Astronomy as well as the Department of Earth and Planetary Sciences. She received her PhD in her native country, Holland, at the University of Leiden. I think her degree was in 1980. Well, I should say, maybe I shouldn't really say that the numbers are always problematic. So her PhD was on the nature of synchrotron emission and non-thermal emission from Jupiter's atmosphere. And she then continued really studying of Jupiter and studied particularly thermal emission from Jupiter. And for the last 15 years, she's basically used every high-resolution radio and infrared telescope that we have to look at solar system objects. And in fact, she has worked just about every object in the solar system, including EOs, volcanic activity, tidings, weather, planetary rings, Saturn and Jupiter, and the giant planets, terrestrial planets, Kuiper planet objects, comets, etc., etc., etc. You name it, she has actually worked on just about everything. And in fact, this morning I asked her, what has she not worked on? And she paused for about 30 seconds and said, nothing. So she put basically all her research into two famous books that she wrote with Jacques Lissor. One is called Planetary Sciences, and the other is Fundamental Planetary Sciences, Physics, Chemistry, and Habitability in 2013. So she has won many awards, to name just a few. C.J. Kwok Award in 1982, the International Radio Science Union John Howard Dillinger Gold Medal in 1984, a NASA Group Achievement Award for Voyager Science Investigation in 1990. She was a fellow, Sloan Fellow. In 1985, she received Miller Research Professorships in 93 and 2003. She's the Ord Professorship at Leiden University in 2017. She has received, together with Jacques Lissot, the 2007 AAS Chambliss Award for writing for their textbook, Planetary Sciences. And also, she's been on many committees, the Gemini Board Directors, the European Science Advisory Board, and on SOFIA, and also ALMA Science Steering Committee, and lots of review committees that she's been also. I don't know how she finds the time to do all this. Today, she is giving a talk on a view of the solar system at radio wavelengths. And please don't forget, we'll have pizza at the end of the hour. Please, Imke.
Okay, thanks, Farhad, for the nice introduction. And as Farhad asked me to talk a little bit about radio astronomy of our entire solar system, I decided to at least attempt that. So radio observations, we can sort of distinguish between a few different topics here. We can talk about thermal, which is basically black body radiation from surfaces, subsurfaces, and atmospheres. Just emission and absorption features by molecules, like for atmospheres and comets. and then non-thermal radiation, usually radiation that is emitted from electrons that spiral around magnetic field lines. So when we look at bodies in our solar system, they typically will reflect and absorb sunlight. And when a body is kind of light colored, it will reflect more sunlight than a darker object. And so a darker object is typically absorbing more sunlight and therefore warmer. So if you would be able to measure both the reflected sunlight and the thermal emission, the blackbody radiation, you can in fact determine both the reflectivity, the albedo, AB, and the radius of the object, or the effective radius, because they're both proportional reflected sunlight to the reflectivity times the surface area, and the thermal emission 1 minus the reflectivity times the surface area. So this has been used, and that is why the technique is called radiometry, has been used for a lot of asteroids by combining infrared data with visible light data, and in that way for a lot of asteroids the reflectivity and their size was determined. So to do this a little more accurately, you really have to take into account the solar zenith angle, and there are a few more parameters in this equation that make the equation and the determination of the temperature a little more accurate, like the emissivity and also eta. Eta is a so-called beaming factor, essentially a fudge factor, that depends on the thermal inertia of the body, on its spin state, on surface roughness. You can just put all of that into this so-called beaming factor. So that is a little more accurate than simply these two equations here. So this has been applied to a number of objects, and I start here with some Kuiper Belt objects, like Pluto and Charon, an image taken by Mark Gurwell with the submillimeter array, and here's another Kuiper Belt object, Huya, taken with ALMA. So the curves here below are model fits to data taken by different instruments and spacecraft like Herschel. The ALMA one is the last point over here and over here. So by using all these different data, you can fit models to them, and as you see, they do actually do a pretty good job. There may be slight differences depending on the exact model that has been used and the input parameters. These are all referred to as the, whatever you call it, near-Earth asteroid standard model fits. Anyway, we'll just proceed. So you can get from these models, for example, ideas about the thermal inertia of the body.
Sorry, Imke, what is the data point? ALMA data point doesn't seem to fit.
No, well,
is there
I mean, it's close enough. But so with ALMA, you probe further down into the subsurface layers. So you really have to get the entire radiative transfer into and out of the surface, subsurface layers. And if there are slight variations, for example, with depth, you may get slight differences. I wouldn't be too concerned about that personally. But so we have observed and imaged Mercury a few decades ago using the Very Large Array. And so for Mercury, as for any other object, during the day, the surface and subsurface will heat up. At night, the heat will be conducted upwards and then lost to space from the surface. So if we look at this graph over here, we see the temperature as a function of the time in Mercury hours. And so at noon, the surface, which is the solid line here, has the highest temperature at noon, and then it will drop off and really sort of instantaneously respond to the sunlight heating up the surface and cooling down the surface. So here at night, and then as soon as the sun starts to rise, the temperature will increase again. So this energy is transmitted conducted downwards. And so when you go down a couple of centimeters or meters into the surface, you notice that it will take time for those layers to heat up. So for example, I'll just take one of the extreme ones at 20 centimeter, where you typically probe down about 10 wavelengths into the crust. So at 20 centimeter, we probe down about 2 meters into the surface. You can see that the highest temperature is reached well after the noon temperature, so well into the afternoon, and then it takes also a while before the coldest temperature is reached, just around sunrise. And when you go down even further, like at 200 centimeter, that is 20 meters below the surface, then you're below the diurnal wave, and you do not see any change in the surface temperature or subsurface temperature. So Mercury is in this interesting spin orbital resonance. That is, when Mercury orbits the planet, the sun twice, it will rotate around its axis 3 times. So every other perihelion, because the orbit is eccentric, every other perihelion, you see the same side of Mercury facing the sun. And in fact, that is either the calorous basin or the opposite side. And therefore, over time, these 2 areas will receive a lot more sunlight, a lot more energy than any other areas on the surface. And so when we then make an image at radio wavelengths, this is 3.6 centimeters, so about 30, 40 centimeters down into the crust, we can indeed see 2 hot spots on the planet, the regions that face perihelion or the sun at every other perihelion. When you model this and then subtract the thermal model, including these hot spots, you ideally would be left with nothing. However, you do see that there are large areas near the poles and along the terminator that are much colder than predicted. And that, we think, is caused by shadowing. For example, in the polar regions you have craters and they are permanently shadowed, and that is in fact where the radar observations have shown the presence of water ice.
How big is this effect in temperature-wise? What are these units in the contours?
Oh, I don't know by the top of my head, but it's of order a couple Kelvin, I think. Yeah, so this is a few decades ago. Sorry. Okay, so let's. Okay, so one of the things that we did derive by fitting such models is that the surface of Mercury actually, there is basalt on the surface, but it is very diminished in refractory materials like iron and titanium, and that has later been verified by the MESSENGER spacecraft. So we'll just continue with some Europa. So Europa, recently people have found plumes on the surface of Europa with the Hubble Space Telescope, and they actually have found these plumes at the same location 2 or 3 times separated by a couple of years. And so that location is just north of this crater in an area just north. And using the Galileo observations, they noticed that that area is either a little bit warmer than the surrounding regions in temperature, or maybe that the thermal inertia is higher. They could not distinguish between those 2 models using just this Galileo point and the different models. So they then used the ALMA telescope. Sam Trumbo and Mike Brown did that, and here is an ALMA image, and this is that spot, that anomalous spot from which the plumes are emanating. And by modeling both the ALMA point and the Galileo point, they could derive that the anomaly on the surface is caused by a higher thermal inertia and not a higher temperature.
So Imke, Europa is the second closest moon of Jupiter, right?
Yeah, it's the second
So,
closest moon of Jupiter, and they're all in synchronous rotation as well. So moving on, comet Halley was imaged by a Giotto spacecraft in '86, and in fact that was the first time that a comet was imaged in detail, and people were kind of surprised that it was not a nice sphere. I'm not sure why, but anyway, it's not at all a sphere, and we didn't really expect that. So we had observed comet Halley, particularly here the OH, the hydroxyl. So OH has been observed in comets for many, many decades, and it's seen sometimes in emission, sometimes in absorption against the galactic background. OH is typically seen in a maser emission, so the high levels in OH are excited by UV light, so there's an overpopulation of the higher energy state, and then it gets the maser emission then gets triggered by background radiation. But depending on the heliocentric velocity, so depending on the velocity of the comet with respect to the sun, Fraunhofer lines on the sun may either move into or out of the excitation frequency. And so if there is a Fraunhofer line at the frequency that the OH should be excited, then there is no excitation, and in those cases we will see OH in absorption against the galactic background. So we imaged comet Halley at the time with the VLA. Here's an image at a low spatial resolution. Here's the spatial resolution. And this one is taken at a higher spatial resolution. And what we see here is that the emission is very, very clumpy, and that there's no emission from near the nucleus. And so we interpreted that at the time to be caused by a quenching effect, that you have so many molecules near the nucleus that they essentially thermalize the OH molecules, and so there's no longer any maser emission coming from it. And so that is why the emission is suppressed at the center, but you do see it in clumps around the nucleus. Another comet that was actually observed very broadly is comet Hale-Bopp. And you can see this was an incredibly bright and also large comet, here seen above the Natural Bridges National Monument. And this comet was observed really by many, many people. And this graph over here shows the production rate in molecules per second as a function of heliocentric distance. So while the comet was moving towards the sun and then away from the sun, you can see, for example, that the OH coming from water ice, is the most abundant molecule, but does not turn on until about 3 astronomical units from the sun, where the temperature gets high enough for water ice to sublime off the surface. At earlier times, you can, for example, see CO that will turn off well before the 3 AU distance, but also it's not as there's not as much of the CO on the comet as water ice. So there are many other molecules, all essentially parent molecules, that can be observed here at these radio wavelengths. And so, for example, we see here methanol and formaldehyde. We see HCN and HNC, and I point those out because in the next slide I show some ALMA observations by Kordener et al. This is the HNC, and below we see the methanol, and we see here data taken over an hour, so these differ by 20 minutes or so. You can see that the methanol does not really change much over that period, but HNC changes a lot. It is like there are just blobs, jets coming out from the comet nucleus and moving away in some directions, and that was interpreted by HNC being caused in part by a degradation of nitrogen-rich organics, which are released sort of intermittently from specific regions on the nucleus.
What is the cross? The white cross?
The cross is the center of the comet. Yeah. So with that, I will move towards giant planets, and to sort of set the scope of the giant planets, I first want to talk a little bit about cloud formation, because that is important later in the talk when I talk about, in particular, Jupiter and also Uranus and Neptune. So to first approximation, you may think that a giant planet has a composition very similar to that of the Sun. So that is about 85% of hydrogen and 15% helium. Then there are trace gases from trace elements like carbon, oxygen, nitrogen, and sulfur, which are present in these planet atmospheres in the form of methane, water, ammonia, and hydrogen sulfide. So if you look at the abundances, which is just like in the interstellar medium, oxygen, water is the most abundant molecule, and then comes methane, and then ammonia and hydrogen sulfide. So what I'd like to point out here is that the S to N ratio is less than 1. So there's much more ammonia gas than hydrogen sulfide gas in these planets, like on the Sun. So now thinking about a parcel of air rising up through the atmosphere, and the temperature in an atmosphere, just like here on Earth, will decrease with altitude. So at some point, the temperature gets cold enough for a gas to condense out. So when we rise up around the 280 Kelvin or so, we get water to condense out, and then at 273 we get water ice to form. At higher levels, we get one molecule of ammonia combining with one molecule of hydrogen sulfide, and that forms a solid NH4SH cloud layer. So that cloud layer will form until all the hydrogen sulfide is locked up into this cloud, and you only have ammonia gas above the cloud. So at about 140 Kelvin, ammonia will freeze out and form the ammonia ice cloud layer. So the topmost layer is ammonia ice. So let's look at some spectra here of Jupiter and Saturn to see how spectra compare with what I've just told you. So the main source of opacity in these giant planet atmospheres is ammonia gas. I mean, there are other gases that absorb, but the main source is ammonia gas. And so when we look at Jupiter and Saturn, and here are the data points, pretty old data points, the dashed line is for a solar composition atmosphere. And really, that does a pretty good job. You can tweak it a little bit as done in these calculations here. But overall, you see that the ammonia gas is very close to the solar value, a disk averaged number for Jupiter, and maybe twice as much for Saturn. So now we go to Uranus and Neptune, and there the situation is very, very different. The solar composition model, again the dashed line, is way too cold compared to the data. Well, that's a problem. That means that somehow there's less ammonia on these planets than we even see on the Sun, as the nitrogen component on the Sun. So in order to start to match a model spectrum to the data, we increased basically all the heavy elements except nitrogen by a factor of 10 on Uranus and 30 on Neptune. So what that means is that getting back to this cloud model, that in the NH4SH cloud, instead of hydrogen sulfide being completely locked up, we now lock up all the ammonia gas. And so above this cloud, there is no longer any ammonia gas present, only H2S. So that means ammonia does not absorb very much, and so this curve then gets up to the cyan curve. So indeed, much higher temperature, but too high compared to the data, at least at these short centimeter wavelengths. So that is when we decided that there's probably another source of opacity, and hydrogen sulfide does have absorption lines at millimeter wavelengths, and we probe several bars deep into the atmosphere, so the lines get pressure broadened so much that indeed hydrogen sulfide is a main source of opacity on these two planets, and when you add it all together you get a red line over here, which is a pretty good fit to the data. And later lab measurements indeed verified that hydrogen sulfide is a good absorber at these centimeter wavelengths. So we observed Neptune in 2003 at different wavelengths, at near-infrared wavelengths. These are adaptive optics images, and you can see cloud features. At mid-infrared wavelengths, where one of the things that stand out is a warm south pole, and at radio wavelengths, where we also see a warm south pole. When you subtract a uniform limb darkened disk from the radio data, you can clearly see that warm south pole very well. And the only way to actually model the data is to assume that the hydrogen sulfide is much less abundant over the south pole than at other places. So based upon these data, we put together a circulation, global circulation model of Neptune's atmosphere, where gas is rising at mid-latitude. So this is pressure. This is 1 bar, 0.1 bar, which is the tropopause, and then down to here 1,000 bars. Here we indicate the various cloud layers: the water cloud, the NH4SH cloud, H2S ice, and then methane ice, which is the top cloud layer on Uranus and Neptune. So we assume here that gas is rising at mid-latitudes and giving rise to these cloud features that you see at the mid-latitudes, both in the south and the north, descending over the polar regions and the equator. And so over the polar regions, at mid-infrared wavelengths, where you probe the stratosphere, you get adiabatic heating, which really is increasing the temperature in the stratosphere. And that is why the temperature at mid-infrared wavelengths is higher over the pole than over the than at other regions. At radio wavelengths, we see this downwelling, basically dry air, because in the upwelling branch the gas is condensing out, so you just have dry air descending here over the pole, and it really does descend down to about the 40 bar level. So you have a circulation that really goes from high in the stratosphere, about a millibar or so in the stratosphere, down to 40 bar depths. So that fits the data pretty well. It's not ideal because there are a few things which we won't talk about here that do not quite fit that circulation model, so we are still working on potential updates on this model.
Is that a uniform convection, or
that's what was assumed here? Yeah,
or do you
uniform global circulation.
Going along for the ride.
Right.
But why don't you see it symmetrically on the opposite?
Oh, you do.
pole?
I mean, in this model you do, but here the North Pole is hidden, so we don't see it.
Right.
Yeah. So Neptune or Uranus. So you may have noticed earlier on, there are here a lot of data points on Uranus at about 3.5 centimeter. And the error bars are much smaller than this entire range is indicating. You see the same thing here at 6 centimeter. So if we plot those data as a function of time, we see that there is a very nice kind of sinusoidal-like curve. So apparently it's not a problem with the data being so spread out, but there is something else going on. So over time, in about 20-year time, we go really from a minimum around 160 Kelvin up to a maximum disk average temperature of about 240. So at the time we interpreted that as perhaps being caused by the polar regions being warmer than the equator. And then when we could make, and this was done by Mark Hofstadter and Brian Butler, when we could actually image Uranus with the Very Large Array, we indeed see that the polar regions are warmer than at other latitudes, and that is indeed causing the variation over time. So I'll just move along with to the next planet, and here we go to Saturn. So these are VLA observations of Saturn, of the disk itself, where you can see a zone belt structure, so warmer and cooler layers, bands on the planet itself, and we can see the rings. Of course, Saturn is best known for its ring structure, and we can really see the rings very, very well, both in the older data and newer data with the upgraded Very Large Array. Well, when we take this picture and we flip it over east to west, and then subtract it from the data, you would see nothing if, in fact, the rings would be uniform and symmetric. But instead of that, we do see a slight enhancement and a slight decrease in the emission, and similarly over here, slight enhancement and decrease. And that has been interpreted to be caused by essentially a larger density of the particles at those areas in the rings. They're referred to as wakes.
Excuse me, the lower left image there with the black,
Yeah?
it somehow reminds me of the spoke.
Yeah, it's not a spoke, but yeah, no, you're right. The spokes are radial; they just move radially outwards, and this is more along the rings in this case. So, another thing that we can do with these images is to look at the ring composition. So the rings are composed primarily of water ice. But there is a very small fraction, about a 1 to 2% effect, of material that is not ice, like silicates, rock. And that there is some radial variation even in that as well. But if you assume that originally the rings were just pure ice, and that it's meteoroid sort of pollution that is making the rings dirty over time, then you can model and calculate that the rings should only be of the order of 100 to 200 million years old, and not 4.5 billion years. So the rings most likely did not form at the same time as Saturn, but were formed much later, maybe by an asteroid that was captured and then fractured, or a moon that came too close. In the middle of the C ring, there is a slightly higher non-icy material fraction, and that is, at least has been attributed to an asteroid, or basically a centaur. So it's an object that is in transition from a Kuiper Belt object to a comet. That crashed into Saturn, and only about 10 to 20 million years ago.
Excuse me, go ahead.
But so it's very interesting how much you can actually derive from such radio data, and of course in combination with detailed modeling.
Just a question about the rings radio emission. I mean, it's
so
it's not really thermal emission.
So the radio emission from the rings, is a good question, is primarily reflected Saturn radio emission. So most of what you see is Saturn's radio emission reflected from the rings, and then there is a small component of the thermal emission from the ring particles themselves, and that gets more prominent at millimeter and submillimeter wavelengths.
Do we know that it's a scattering essentially? Is it a forward scattering, or what's do we have a sense of what
so
the
the models we use, it's sort of Mies scattering and isotropic scattering. It's a combination.
Mm.
So this is a map of Saturn's atmosphere constructed from Cassini 2 centimeter data. So it's still radio data, but taken with a spacecraft. What we see here is a lot of course, latitudinal structure, but in particular this big band stands out. And then there is the rings actually over here, the dark area here. So what we see here is the brightness temperature. A uniform limb darkened disk has been subtracted. So where we see bright areas, we see a higher brightness temperature caused by, presumably, a lower ammonia abundance, so you can probe deeper layers in the atmosphere, whereas the more gray and darker areas show lower brightness temperatures, so probably more ammonia gas. So this region, this was imaged in 2011. In 2010, 2011, there was a large storm, once in a 30-year storm on Saturn, which really encircled, after it had started, the entire planet. And that is what is causing this variation in the ammonia abundance. And that low ammonia abundance has been seen for several years after the big storm actually already dissipated. So with that, I want to spend the rest of the time on Jupiter and talk a little bit about sort of more recent observations that we have made of Jupiter's atmosphere below the clouds with the upgraded Very Large Array. So at different frequencies or wavelengths, 1.5 gigahertz or 20 centimeter wavelengths, up to here 17.5 gigahertz, about near 2 centimeter, we probe depths in the atmosphere from about 0.6 down to 20 or 50 bar level. So for comparison, the cloud layers are shown over here. So we probe well within the ammonia ice cloud layer to well below even the water cloud layer. So we have used the Very Large Array, and typically at the different frequencies in two configurations. One which is an extended array where you just get sort of the UV data at larger distances, and a more compact array where you can actually see the entire planet. So you can combine the two. It's not easy because Jupiter is moving and rotating, changing all the time. But anyway, you can try to combine the data and then get a full picture of the planet. So just for background, Jupiter, of course, the largest planet in our solar system, and it consists basically of about 85% of hydrogen and 15% helium, and then the trace amounts of methane, ammonia, water, and hydrogen sulfides. So Jupiter is rotating, and the different zones and belts, winds, also cause the features to move relative to each other as well. So this is where the great, sort of centered on the great red spot, but you can see that everything is just moving with respect to everything else. So you can imagine that actually imaging that is not straightforward. So one of the fundamental questions for Jupiter, as for all the other solar system bodies, is that we ultimately want to find out how our solar system formed. And for that we want to know what the composition of any body in our solar system is, because that gives us information on the conditions of the solar nebula during the time that the sun and the planets formed. And that, of course, we can then determine through either remote sensing or in situ sending a probe there. And of course, a probe has been sent to Jupiter many years ago, the so-called Galileo probe. But before that, we can look at different wavelengths, visible, 5 micron, and radio, to probe different levels in the atmosphere. So here we have the altitude versus temperature, and that is for this temperature pressure curve. And again, we have the cloud layers, so that the water, the ammonium hydrosulfide, and the ammonia ice cloud. So if you probe visible wavelengths, you of course see the topmost cloud layer, the ammonia ice cloud layer. If you look at 5 micron, we can probe down to depths of about 7 or 8 bar depth, so almost below the water cloud layer, at places where there is no clouds. So that is why you see enhancements at different parts. And then in the radio, we can also probe down below the cloud layers, and this is an image from the VLA in quite a while ago, the mid-90s. This is averaged in longitude because you have to build up enough signal to noise, so you have to integrate while the planet is rotating. So the deepest layers really are probed at radio wavelengths, where the clouds are almost transparent. And again, the opacity is dominated by ammonia gas. So we can probe down at very long wavelengths, down to maybe hundreds of bar pressure, except from the ground. We can't really do that very well, but that is where a spacecraft comes in handy. And I'll talk about that in the end of the talk.
So the dark regions in the infrared image is just due
Clouds.
to opacity?
Yeah. So it's clouds, so you probe very high layers in the atmosphere where it's cold, and the bright regions you probe deeper where it's warm. So it's just the temperature that you see. Okay. So the Galileo probe measured the abundances on Jupiter in one particular area, actually in this so-called hot spot, which is indicated by a little arrow. And they found that for most of these elements, like argon, krypton, xenon, but also carbon, nitrogen, and sulfur, the abundance is several times higher than that of the solar abundance. Well, in the radio, I just showed you these spectra, and that showed that ammonia gas really is very close to the solar value, so very different from the Galileo probe value. And water they have not been able to measure with the Galileo probe at all. So there are two questions that surface. And one is, what is really the water abundance in Jupiter's deep atmosphere? And how can we reconcile this difference between the radio measurement and the Galileo probe measurement? And that is where we go back to our picture here of air rising in the zones and descending in belts. We really measure sort of the ammonia abundance as a function of depth. So if we look here at the ammonia profile, when ammonia gas is rising, at some point, well, first you lose some ammonia in the water clouds, then you form this NH4SH cloud layer, and finally ammonia is condensing in the ice cloud. So you should be able to see actually that profile if you have good enough data. So now looking at the spectrum using data from the Very Large Array, and just look at the solid red points here, what we see is that this cyan profile that has the Galileo abundance at deep layers and then just going up via a normal chemical model, that is way too cold compared to the data. A solar composition model, this blue curve, is too warm. And so really what you see is a profile kind of like this red one, which somehow you need to lose ammonia gas from what Galileo measured to where the VLA is sensitive to. So how then can we lose ammonia gas between these sort of upper level 3 to 3 bar down to the 8 bar? It could be chemistry, we don't think so, or dynamics somehow. If it is dynamics, we should get a large ammonia abundance over these zonal regions where gas is rising, which we had not seen so far. So with the newer VLA observations, this is a composite of different wavelengths after subtraction of a uniform limb darkened disk, and we see bright belts where we probe deeper in the atmosphere, less ammonia gas, and the darker zones where we probe less deep. And all the way around, and I won't really talk about it, is synchrotron radiation. So that is radiation emitted by electrons trapped in Jupiter's magnetic field. And here are some gorgeous L-band 20 centimeter data of that synchrotron radiation.
What's causing that polar dependence on the polar angle, the segregation? Is that all convective zones? You've got all those bands across them, right?
Yeah.
And they're stable with time, year after year.
No, they're not.
This is a snapshot.
I mean, this is a snapshot integrated. Well, it stays the same over weeks, maybe months time scales. Yeah.
Are they convective cells, up, down?
The zones, it's convective upwelling. Yeah.
So you're going to talk about how you generate electrons. Sorry, go ahead.
I'm not talking about non-thermal
Synchrotron,
radiation.
okay.
So when we look at the spectrum of different zones and belts, here I look at a spectrum here from the VLA of this north equatorial belt region versus a spectrum of the equatorial zone just south of it, the darkest area. And when you model that with these models, we see that for the zone, actually the Galileo profile fits very well. So over the zones, you do see that ammonia gas at the concentration detected by the Galileo probe is brought up from deep down to the higher levels. The North Equatorial Belt, the belts are really very much depleted, and that is kind of indicated by this red curve here and even subsaturated higher up. So we put everything together and try to model the ammonia abundance as a function of latitude, where we adopted this Galileo probe ammonia abundance at pressures larger than 8 bar. And so this is very, very preliminary. But what it does show is that near the equator, you have indeed gas being brought up to the high altitudes. Near the polar regions, you get depletion of ammonia gas. And then you get areas, basically the zones on Jupiter, where you have a higher ammonia concentration than the belt regions. And you can see also actually here where the NH4SH cloud layer kicks in. So that's nice, but what we really like to do is to see what a longitude resolved image would give us. And I think in the interest of time, I will not go through this, but you can ask me later. Anyway, we are able to produce longitude resolved maps of Jupiter. And here we show a map at 2 centimeter wavelengths and flip it back and forth with an amateur map based upon visible light images taken by amateur astronomers. And this is also put together, the visible light, by the amateur astronomers. And you can glare at this, I mean, just forever. You can really see a lot of things in the radio very sensitive to ammonia gas, similar to what we see at visible wavelengths. So we see the great red spot very clearly. We see little oval BA very clearly. We see this sort of very radio hot belt, which coincides with the boundary between a brown belt and white zone region. And in that we see a lot of features in the radio that correspond to hot spots, like the 5 micron hot spots that have been detected a long time ago. When we look at 6 centimeter wavelengths, we see a completely different picture. We see, well, most striking is these very large dark areas, which we refer to as plumes. So these are areas where ammonia gas is brought up from the deep atmosphere to the high altitudes. Because ammonia gas is the main source of opacity, we see very low temperatures there. And interspaced with that are these sort of high temperature hot spots in the region. We also don't see much longitudinal structure. You can make out here the great red spots. But at 2 centimeter you see a lot more structure. You see a lot of little ovals, etc. Spectra of these hot spots and plumes, here the hot spots and the plumes, again, basically show what I just said in words. In the hot spots, ammonia is depleted to deep levels, at least to 8 or 10 bar level, and in the plumes, we really get saturated ammonia gas being brought up from below. So we happen to have 2 observations at both at X-band, 3.5 centimeter and 2 centimeter, separated by 2 weeks. So we looked at the velocity of these plume regions, and you can just indeed identify the same ones at those 2 different images. And from that we derived that the phase velocity of the plumes is about 100 meters per second, which is the same velocity as had been measured for 5 micron hot spots many, many years ago. And that was interpreted as being caused by a Rossby wave. And so what we see in the radio is the counterpart of the Rossby wave that is causing the 5 micron hot spots. And here is a numerical simulation of that by Showman and Dowling, where you see hot spots interspersed with our plumes. Very neat. So for the radio, just a very quick summary, and then I want to show some of the Juno observations. So we see large variations in the ammonia abundance across the disk. We see lots of vortices, small-scale features, but all at pressures less than about 2 to 3 bars. So that's really the weather layer on Jupiter. We see this radio hot belt with the hot spots, the Rossby wave, and then because we see this ammonia gas being brought up from deep below to the high levels and then dry air descending, we think that that explains the conundrum between the ground-based observation of ammonia gas and the Galileo observation. So let's quickly look at some of the Juno results. Of course, I mean, there are the spectacular images at the visible and the near infrared, where you see the auroral emissions. But what I'd like to concentrate on is the MWR, the microwave experiment on Juno, which is an experiment based. They measure the radiation between about 1.4 and 50 centimeter wavelengths, and really can go down to hundreds of bars pressure level. Their goal is to determine the 3D ammonia and water abundance. So Juno's field of view, however, it's a polar orbit, is very, very tiny. It's shown over here. So basically, it's flying in a polar orbit and seeing a very small footprint on the planet. And in that footprint, they will measure the brightness temperature at these different wavelengths or different depths in the atmosphere. But they don't really know what they're looking at without context images. So of course, images like we have with the VLA, those are the best context images to figure out where actually that Juno is looking at, whether it's a plume or a hotspot or whatever. So we can compare our ammonia abundance distribution with latitude with what they published a few years ago. And overall, there's a good comparison. We both see this large ammonia sort of plume near the equator. But then there are many differences as well. They see a lot of ammonia gas at high altitudes. They see a minimum here near the water cloud region, which we do not see. They also see a concentration of ammonia gas in the deep atmosphere that is much less than what Galileo probe had measured in situ. So there really are a lot of puzzles that at this point in time we do not understand, but we hope by combining Juno and the VLA data that someday we will be able to understand those differences. And with that I come back to the overall slide of different radio observations of our solar system and the talk here.
Thank you so much for a nice talk, and we have time for questions. Yeah, go ahead.
Do you have any speculation on how they can be reconciled?
Not really, but we can talk afterwards.
But could it be time variability a part of this?
No,
it could not be a time variability.
No, I can talk afterwards about it.
Yeah. It's so I had a question about how you observe these objects, solar system objects, and you make these nice images, while all these sort of solar system objects are moving quite rapidly. What kind of technique do you use with radio interferometry to image these objects? Because the quality of the images cannot be really great because things are rapidly moving and changing.
That's why I'm trying to to find my mouth. Well, maybe. Okay, so you have to integrate for a long time to build up enough signal to noise to image a planet. You can easily follow the planet with the dishes. So, for example, if you do want to observe something like the Great Red Spot, as you have seen we have done in the radio images, we basically use a technique that Bob Salt had developed by manipulating in the Fourier domain, adjust the phases so each feature is tracked, basically stays at the same position on the sky, and then we essentially image that tiny region, and then later we kind of stitch all the data, all the maps together to produce that large feature. But as you can see over here, you can have a nice cross here at the center, but if that cross is projected onto your sphere, you know exactly how it is projected and how you can deproject it. And so in that way, Bob figured out how to adjust the phases and in the UV data to ultimately combine enough data so you build up signal to noise on the individual features.
How much is the time that you're observing for each individual? Sort of the snapshot, series of snapshot.
Yeah, so for Jupiter rotates in 10 hours, and so we typically have observations over a full 10 hours if it's up that long. And in many cases we actually do frequency switching, so we can do, say, 2 centimeter and 3.5 centimeter sort of during the same run. Yeah.
Other questions?
Does it rain on Jupiter?
It depends on what you call rain, but we have.
Is there precipitation? And do you have ammonia rain and water rain?
So we can only say anything with that for certain based upon theory. Right? We haven't really gone down and measured rain. I mean, the one place where the Galileo probe went down, it was a hot spot, and so it didn't even see many clouds. But better and we think the water cloud, there is a liquid water cloud down there, but
You talked about ice clouds and water,
Yeah,
et
so-
cetera, and
right,
if
so-
they get big enough, they fall. So.
Right, and people are trying to model that, but that is really in infancy. But it is a very important area. Now we get data that are as good as these. Because
weather forecasting on Jupiter is an emerging topic. isn't
yeah,
it?
it's an emerging topic. And for example, if you do look at if indeed this is real and there is a minimum here in the ammonia abundance, then somehow you might think that there is transport, latitudinal transport, where ammonia, say particles, are moving sideways at lower and higher latitudes, and then if those grains, the ice grains, fall down, they will sublimate, and that might explain the higher ammonia concentrations over here. If that's true or not, I really don't dare to say at this point. But those are so indeed the raining of ice particles, the bringing up the ice particles, and the lateral motion and then subsiding has a lot of what you refer to of condensing and sublimation, raining, etc.
Just a quick question. I know you weren't going to talk in detail about the synchrotron emission, but I was wondering, is that a feature that's seen in other gas giants as well?
So synchrotron radiation really is unique to Jupiter.
Okay.
So we've only seen it on Jupiter. In Saturn, in fact, the particles which might lead to synchrotron radiation would all be absorbed by the rings because they bounce up and down the magnetic field lines.
Okay.
I'm glad you asked this question. Yeah, go ahead.
Do you have anything on Venus?
Well, we've observed Venus, a long time ago, where in the radio we did see a day-night contrast, and we interpreted that at the time by variations in the, I think it was in the sulfur dioxide concentration of gas, and basically, it's a long time ago. So basically, sulfur dioxide is thought to be brought up by volcanoes. In fact, now they think there might still be active volcanism on Venus, but the combination, the chemistry of that gas with other gases on the planet may lead to particles condensing out and not condensing out. So we could ultimately reconcile the day-night contrast on Venus, and that is something that still seems to hold, that theory. But I forgot the details. It's a long time ago, 30 years, I guess.
So you can do a lot better with ALMA these
Oh
days.
yeah.
If you do
I think people are observing Venus with ALMA.
Yeah. Okay, with that note, if there are no other questions, let's thank the speaker one more time.